What's up everyone, Patrick here, welcome back. Moving on to another question dealing with trigonometry. This one's actually going to combine trigonometry and quadratics a bit. So we're told that a right triangle's shortest sides differ by 17 centimeters and that it has a hypotenuse of 53 centimeters. And what we have to do is we have to use two methods to find the shortest distance from the hypotenuse to the right angled vertex. So let's draw, as usual, a diagram of what we're working with. So we have a right triangle like this. Here is the right angle. I'm actually not going to draw that right angle there yet because I want to show visually a little bit more clearly what we're going to be doing. Now, we're obviously going to have to find the sides. We are given the hypotenuse, the length of the hypotenuse, which is 53 centimeters. But notice that we don't know what these sides here are, but we know that they differ by 17 centimeters. So for example, if we let this side be x, we can let this side be x minus 17. And that's where the quadratics are going to come into play. If you remember from that unit, we did questions where we had to find the dimensions of a right triangle. And we were given certain descriptions of the parameters. In this case, these two sides differ by 17. You could also let this be x plus 17, for example. But in this case, I'm letting this one be the longer of these two sides, so x minus 17 is going to be the shorter one. So first we're going to have to find the sides. Now, eventually what they're asking for is to find the shortest distance from the hypotenuse, which is this line here, to the right angle vertex. So the right angle we know happens here. This is the vertex of that right angle. And so what we have to do is we have to find the shortest distance from this point to the hypotenuse. We have to do it in two different ways. Well, if you remember when we dealt with geometry, we were finding the shortest distance from a point to a line. And if you remember, the shortest distance from a point to a line is always going to be the perpendicular distance, right? And so that's what we have to find here, this distance right here. And there's going to be multiple ways to do that. As you could see, it creates two new triangles that are both right angle triangles. So that's a hint of one of the methods we're going to use. But there's also a pretty cool other method that we can do to find this distance. And it's kind of a cool way to show how no matter which method you use, you're going to come up with the same solution. So eventually that's what we're going to have to do. We're going to have to find this distance here, right, from here to here. That's the shortest distance, the one that makes the one where the distance line makes a perpendicular angle with the line you're finding the distance to. So eventually we're going to have to find that. But first, before doing that, what we have to find is these actual sides here, because if we don't know those sides, we're not going to be able to find that distance right there. So to do that, what we could do is set this up as a Pythagoras theorem, right? If this is the right angle triangle, we know that a squared plus b squared is equal to the hypotenuse squared, c squared. So we could say this side squared plus that side squared is equal to 53 squared, like that. So this would be x squared plus, now if we take x minus 17 times x minus 17, right? If we take that, if we FOIL it out, you'd end up with x squared minus 34x, right? The negative 17x minus 17x, that simplifies to negative 34x. Then negative 17 times negative 17 gives us 289. And then 53 squared would give us 2,809, like that. And so from here, what we can do is this ends up just being a quadratic equation. So these are like terms. So that'll be 2x squared minus 34x. And then this 2,809, I'm going to bring over 289 minus 2,809. That would give us what? Minus 2,520, like that. And now notice you have a quadratic equation to solve. I think this will actually factor fairly smooth. You can actually take out a 2 from this, and then this bracket will factor, but they're fairly large numbers we're dealing with. So because we're not really focusing too much on quadratics, at this point you could just throw this in the quadratic formula if you want to find those x values that satisfy this equation. Now, if you want to go and practice your factoring, you can. From here, I'm just going to put in the quadratic formula, which is negative b, so it's negative 34, plus or minus b squared, so negative 34 squared minus 4 times the a value of 2 times the c value of negative 2520, like that. And that's going to be all over 2 times the a value of 2. Now you could also take out a 2 from this and you'd be left with a quadratic, and you could throw the parameters of that quadratic into this formula. You would get the same solution. And if you go into simplifying this square root here, everything under the square root would simplify to this large number, 21,316. We got the 34 over here, the negative turned into a positive, and then 2 times 2, we have the 4. And then the square root of this gives us 146. It's actually a smooth number. And then we have two solutions because we have the plus and minus, and we end up with two solutions, 45 or negative 28. But notice, remember, x represents the length of this right angle triangle, so it can't be a negative value right here, right? That would be an inadmissible solution. So the answer is 45. So this would be 45 right here. Right, this length is 45. This length would be 45 minus 17, which is 28, like that. So now we have the full dimensions of the right triangle. We did it with quadratic equations. And then you could confirm this. You could confirm these dimensions because you could plug them in to the Pythagoras theorem, and you just got to make sure that the Pythagoras theorem is going to hold. And if you do 45 squared plus 28 squared equals 53 squared, when you do this algebra, you'll end up having both sides equal to that 2,809. All right, so they are legit sides of a right triangle, 45 and 28 right there. And from here, we can actually now go into finding that shortest distance. Quick little intermission here. I wanted to mention a few things and we'll get right back into the video. Number one, if you're watching this on YouTube, you can go to the description box and there's a link that will take you to my website, allthingsmathematics.com, and there you can find all of the videos organized by chapter, by section, and there's also tests that you could try at the end of each unit. Number two, if you feel like you need tutoring at any point, I'm tutoring students 7 days a week over Zoom, both high school and university students, one-on-one and in groups. My contact details are on the website. You could text me and we could book a session. And finally, if you feel like you're getting any value from this video, if you could please like the video and subscribe to the channel, hit me up on all my socials. It does help me out a lot. If you feel like any of your friends can benefit, feel free to forward the website to them as well. And back to the video we go. So let me erase this just so there's a little bit less going on. Now, a couple of things we can do. Now, one way, this is not going to be using trig ratios. The second method I'll show you will use trig ratios. Is, again, let's just draw this line here, the shortest distance line from this point to this hypotenuse. And remember, it's going to make a 90-degree angle like that. Well, if you think about it, if we sort of take this triangle and if we rotate it, so we would have a triangle like this. This would be 53. Let's say this is 45. This is 28. Well, the line that we just drew here is basically this line. And notice that that right there is like the altitude. It's like the height of the triangle. So notice that we can create, we know that the area of a triangle is what? Base times height divided by 2. So notice that in this particular drawing, the base of the triangle is the 53. So that's the base. Then we have the height. We don't know that. That's actually what we're solving for. And then we're going to be dividing by 2. That's the area. So you might be asking yourself, okay, but at this point, we don't know what the area is, right? Because here we have two variables in this equation. So how are we going to solve this? Well, let's get rid of this. So this I drew over here, right? This is the line we're solving for. Let me get rid of this line. Well, this is a right triangle, if you remember, right? This is 90 degrees. And notice that we can get the area of this triangle in another way if we let this side be the base and this side be the height. And that would give us the area because we know it's 28 and 45. So another way to get the area of the exact same triangle is doing 28 times 45 and then dividing it by 2. And when you do this calculation, you'd end up with 630, like that. So the area of this triangle is actually 630 centimeters squared, base times height, divided by 2. But we can represent this area in another way if we let the 53 be the base and we let this altitude here, which was this line that we drew, which is actually the length of the line we're trying to find, the shortest distance from that point to that hypotenuse, we can let that be the height over here. So base times height divided by 2. And it's because it's the same triangle that we're dealing with, we know that this area has to equal 630, the area that we just calculated the other way. So we could take this 630, we could plug it in here, and now notice we have only one variable to solve for. And so to solve this, what we can do is we could put this over 1, cross multiply, so we'd have 1 times 53h, so that's going to give us 53h, 2 times 630, which would give us 1260. Then we could divide both sides by 53. What do we end up with? 23.77 centimeters. And so that actually ends up being the answer to this question. Remember, this height that we represented here is the same as this line, which is the shortest distance from the right-angled vertex to the hypotenuse. So that's the solution. So that's how we got the solution with the first method. And so let's see if we can get it with the second method. Now I mentioned with the second method, we are going to be using trig ratios, right? And so it's going to use the new right angle triangle that we create over here. So we could use this one as well. I'm going to use this right angle triangle that gets created like that. Okay, so if I take this new right angle triangle and if I draw it here, okay, if I sort of rotate it, we know that this is 45, which is the hypotenuse of, right, this here is the hypotenuse of that new right triangle. So I'm taking, one more time, this right triangle here, and I'm rotating it a bit to get this. And so what we're solving for is this side from here to here, like that. We're going to be solving for that side right there. The question is, how can we do that? Because we don't know what these angles are, right? We don't know what this third side is, which is this side from here to here. We know that this total side is 53, but we don't know what this side is. So the question is, how can we solve for this x value? Well, notice that we can solve if we look at the larger right angle triangle that we started with. So let me actually hold up before I erase this. So if we look at the larger right triangle, we can solve for this angle theta, because in the larger right triangle, we have all 3 sides. We really only need 2 of the sides, but we have all 3, so we can solve for this theta in different ways. And notice that this angle theta, if we come back to this triangle, that's the same as this angle theta, right? And so once we get this angle theta, then we could solve for this x value. Okay, so what I'm doing, let me erase this, is I'm taking our original right triangle. Let me get rid of these variables too. So there's just less going on here, right? We're taking our original right triangle with sides 45, 28, and 53. We're going to solve for this theta. Okay, we can use it using trig ratios, right? This is the adjacent, the opposite, the hypotenuse. We have all 3 sides, so we could use any of the 3 ratios. We could solve for that theta, And then we could use that data here in this triangle that we create and solve in this new triangle for that x value, like that, for this x value, which is going to be the distance from that vertex to that hypotenuse. Right? Hopefully with all this explanation, you kind of get what's going on by now. So we're using the larger triangle first to solve for the theta, and then we're going to use the smaller triangle to solve for that shortest distance. And so you can use, again, any of the ratios. If I use this 45 as the adjacent side, this is the hypotenuse, that would use what? Cos. So we would have cos theta equals the adjacent side over the hypotenuse. So that means theta would be cos inverse of 45 over 53. Okay, but you can also use the opposite and the hypotenuse. So then you would use sine, right? Sine of theta would be 28 over 53. So the theta would be sine inverse of 28 over 53. Or you could use the opposite and the adjacent side, which would use tan. Tan theta equals opposite over adjacent. So then theta is tan inverse 28 over 45, right? You could use any of the three ratios here because you have all three sides. All of these calculations would give you the same angle. And when you do that calculation, you'd end up with 31.89 degrees, whichever of the ratios you use. So that this angle theta is 31.89 degrees, which means this here is also 31.89 degrees. So now we come to this triangle. So now we're going to be working with this triangle, right? So we could actually get rid of this part of the larger triangle right there, right? So this here, right? This is the same triangle that we have right here. And we have this side, which is 45. We have this angle, which is theta, the 31.89 that we just solved for, and we're solving for this value, this x value. Okay, now in this particular case, when we're looking at this triangle, this is no longer the adjacent side that was of the larger triangle. With this smaller triangle, this 45 ends up being the hypotenuse. So let's come over here. So remember, this is the angle we're looking at. This is going to be the hypotenuse, which is across the 90 degrees. And then this side x, which is what we're solving for, notice that that's the opposite side to this angle. And in this particular case, we don't have this third side. We don't have the adjacent side. We're only working with the opposite and the hypotenuse. Which ratio deals with that? That's the sine ratio. So we could say sine of 31.89 equals the opposite side over the hypotenuse, like that. Put this over 1, cross multiply, so x is going to be 45 times sine of 31.89. And then when you do that in your calculator, guess what? You're going to get that exact same solution that we got before, right here, 23.77 centimeters. Right? So those are two different methods in how you can do this, this question. There may be other methods. You can probably actually take this, now that I think about it, probably take this right triangle and put it on like a Cartesian plane. And then you could maybe put this at the origin, like if you flipped it, and then this point here, yeah, you can, with the larger right triangle that we had, you can probably put this at the origin. This here would be at 0 and 45, and then the other point would be at 28 and 0. Okay, and then you could find the equation of this line, and then you find the distance from that line to this point, 0 and 0, like we did in the geometry unit. So that's another method, but I feel like these methods are easier. I feel like the first one we did is the easiest, but I did want to show you the second method because we are dealing with trig ratios in these units. So I wanted to show you a method that uses those trig ratios. So whichever way you do it, 23.77 centimeters is the answer. you get. And that is the end of the video. Hopefully you enjoyed that. If you want to find more videos like this, you can go to my website, allthingsmathematics.com. Over there, all my courses are organized for both high school and university. All the videos are organized by chapter. Also, if you have any questions, you can hit me up. My contact details are also on the website. Enjoy your day, and I'll catch you in the next one. Peace out.